quick little finish up of what we were talking about with molecular velocity. Our brains were probably a little fried by the end of it last time. So we're just going to summarize it again. Okay, so the average mass and the velocity. So remember I showed you this formula, but I'm going to talk about a little bit more about what this formula means this time. So gases in the same container we talked about have the same temperature, right? If they're in the same container, they have to have the same temperature. Therefore, they have the same kinetic energy. So they have the same amount of energy, but it doesn't mean they're traveling at the same speed. Because if you have a heavy gas and a light gas, the only way that they can have the same energy is for them to have different average velocities, right? Because if they have different masses, that must mean they must have different velocities. So if this is going to be the same, and if this number is different, that means velocity is going to be different. So therefore, heavier molecules and lighter molecules in the same container have the same kinetic energy, but they're not moving at the same speed. Light particles are going to move faster than heavy particles. So let's look at some gases to show you how this works. Okay, so this is just the distribution of the speed of the gases. So you can see hydrogen is our lightest gas, and hydrogen travels faster than, so it's kind of, if you look here, the average hydrogen is probably about right here. It travels faster than the other molecules. Now, all of these molecules are in the same container. So this means they have the same kinetic energy, but they're not traveling at the same speed. Oxygen, right, is 32 grams per mole. Nitrogen is 28. Water is like 18.02 grams per mole. Helium's 4-ish. I don't remember the others, 4 mole. And hydrogen's at like 2.016 grams per mole. So this one is the lightest. This one is the heaviest. If you look at like the average of oxygen, here's its average speed. Where if you look at like, let's do helium, it's easier to see. Helium is much lighter, so its average speed is faster. They have the same energy, but they're not traveling at the same speed. All right, so that's just kind of like sum it up, just like we've been talking about before. So if they're in the same container, same energy, not the same speed, right? The lighter ones will always travel faster than the heavier ones. They just have the same energy. Okay, now to gases and stoichiometry. Okay, so we're going to be using the ideal gas law all the time now. Remember, I taught you how to get through all the other gas laws through the ideal gas law, but today we're really going to be talking about the ideal gas law. And the most important thing that we're going to be seeing is if we have something and we want something else, we know we've got to do a mole-mole ratio somewhere, right? Well, if you've got the ideal gas law, you've got moles right there. So a lot of the times we're going to be needing to go from moles of something to moles of something else. We can use the ideal gas law to do so. Okay, also we're going to use volumes a lot here, and again, ideal gas law. Okay, so here's what we did before with stoichiometry. So we had grams of something, we used the molar mass to get to moles, then we did our mole-mole ratio using our balanced chemical equations, got to moles of our other thing, to use our molar mass, got to grams, right? So we've done this again and again and again and again. Well, now we're going to incorporate PV equals nRT. So let's say we have something, but we want something else. We need to get to moles of it, right? The whole goal of this mole ratio, you can see, this is that piece, this really important piece to go from one to the other. So we might have to use PV equals nRT to get to moles, right? And then go from moles of one thing to the moles of other, and then use PV equals nRT to maybe get to a volume or to a grams or something of that sort. So we're going to practice all sorts of pieces of this today. Okay, and I think the easiest way to do these is just to start. Okay, now remember with stoichiometry, the hardest part is setting up the problem. So you have to figure out what you're starting with, what you're trying to get to. That's kind of the key to stoichiometry, right? I've been writing those have and wants like all the time. Now they're really going to become important. Understanding what you're starting with and where you need to go. Remember, this is your guide. This is kind of like your map to what you're doing. So if we read this, it says a sample of hydrogen gas. So it's talking about this right now. Hydrogen gas has a volume of, so I'm just going to write it on this right here, 7.49 liters. It has a pressure of 22 atmospheres and has a temperature of 32 degrees Celsius. And we remember we can't use Celsius, so I'm just going to write the 273 Kelvin right into the problem so I don't forget it. There's a lot to do. I always say you can't leave it all up to your brain. Your hands have to do some work also. Write the plus 273 right away. Now the question says, what volume of gaseous water? Okay, so I'm just gonna put this in a different color. This is asking about water, but originally they gave us all of our information about hydrogen. So they're asking about volume of water. So I'm gonna say liters of water. So that's what they're asking about. So now we already know there's gotta be a mole ratio involved here. Because remember, if you have something and you want something else, you've gotta convert. And the only way you can convert is mole ratios using the balanced chemical equation. Okay, so it says what volume of gaseous water is produced by the following reaction, and it has a temperature of 125, and again, I'm not even gonna leave that 125 there. I'm just gonna put just straight to Kelvin, 0.975 atmosphere. If all the hydrogen gas reacts with the iron 3 oxide. So the iron 3 oxide, this is like just extra information. Okay, so now we have to think. We're starting with hydrogen, but we need to get to water, which means we have to get to moles of hydrogen, right? Because the only way to go from hydrogen to water is a mole-mole ratio. So somehow we have to use these coefficients to go from one to the other. So what do we have about hydrogen? So we
the
have
atmosphere, is that 0.95?
No, I forgot the 7. Thank you. And the T. Thank you. Okay, so if we look at our hydrogen, we have a volume, an atmosphere, and a temperature. Okay, so again, it's gases. So I'm just going to write PV equals nRT to figure out what do we have. So we have a volume, check. We have a pressure, check. We have a temperature, check. And we always have R's. Oh, so what I just found out was I can use PV equals nRT and I can solve for N. Right? Divide by RT, PV over RT. I can get to moles of hydrogen here. Well, once I get to moles of hydrogen, I can convert from moles of hydrogen to moles of water. Okay, so that means then I'll have moles of water. I'll have it. I don't know what it is, but I'll have it. I'll have my moles of water. Then I can look here. If I have my moles of water, I've got a temperature right there. They gave me a pressure right there, and they're asking for a volume. All I have to do is solve for my volume. So now the next part is not so bad. It's this right here, this plan that we just formulated, and the thinking of what do we have? How are we going to get to what we want? That's the key to these problems. Number one, we started with hydrogen gas, but they asked for the volume of water. So somehow we have to get to moles of hydrogen so we can convert to moles of water, right? That was our first hurdle. Figured out we could use PV equals nRT. Then we can convert from hydrogen to water, and then we use PV equals nRT to get to volume. Okay, so that's our plan. Now we just have to execute it, which don't really have a lot of room here. So here's kind of everything we just talked about. And again, you'll see I just wrote my temperature straight as Kelvin, right? So the first one's 305 Kelvin and the next one's 398 Kelvin. And you're gonna see here, like I used 0.15, 273.15. Again, you can just use 273 or you can use 273.15, depending on the book and depending on the chemistry professor. Everybody kind of like a 50-50 split on what people use there. So I want you to see both. When you're doing your problems, feel free to use either of those. Okay, so here's our plan. We're going to use PV equals nRT to get to our moles of hydrogen. From there, we're going to do our mole ratio, which we can already see our mole ratio is going to be 3 hydrogens to 3 waters. Then we're going to get to our moles of water, and then we're going to use PV equals nRT to solve for our volume of water. Okay. By the way, if you can do this faster than I can, go for it. And you can just type your answer in the chat or write it down on your piece of paper. Okay, so here's everything we're given. And you can see now, remember how I talked about how once you take the numbers out of the words, you don't need them anymore? I don't necessarily need the problem anymore. I've got all my variables here. I don't need to reread it anymore. So first we need to get to our moles of our hydrogen gas. So we said that was N equals PV over, you know what, I'm just going to start all at the beginning. PV equals nRT. We're going to solve for moles, so divide by RT, divide by RT. So that means that N equals PV over RT. Our pressure is 22 atmospheres. I'll worry about my sig figs in the end. Our volume, 7.49 liters. Our R, I think I'm going to use the big one, 0.08206, and the units are liter, atmosphere, mole, K. And then our temperature, 305.2 Kelvin. This is going to give us our moles of hydrogen, right? So that's our step 1, moles of hydrogen. And I know everyone knows how to put this in there. So you end up with 6.58 moles of hydrogen. I already solved this one, so that's how I remember that answer. Okay, now we have our moles of hydrogen. Remember, we want water, so we're going to convert from hydrogen to water. So if we have 6.58 moles of hydrogen, we're going to convert to water. So there's 3 moles of hydrogen to 3 moles of water. So in this case, we end up with the same thing. That's just chance, though. So we have 6.58 moles of water. But remember, we want volume of water. Okay, so now we need to find our volume of water. So PV equals nRT. We have a pressure. We have a temperature. Now we have a moles. We have an R. We just need to solve for our volume. So divide by P. Divide by P, V equals nRT over P. Okay, so V of water is nRT over P. So I have 6.58 moles, 0.08206. I'm not going to put the whole unit in this time, times new temperature, 398.2 over P, 0.975 atmospheres. Right? And then we just put it in our calculator. And I don't remember what you get. I think 221, that sounds about right. Okay, So again, I'm not even going to think about my sig figs until I get to the end. This one has 3, this one has 3. 3 seems to be the minimum. I'm going to use 3 sig figs. Okay, so this right here, just a PV equals nRT problem. PV equals nRT problem, mole ratio problem. We're just putting them all together now, right? So we're kind of doing everything at once. Okay, so now I'm going to show you this much neater than what I just wrote. Okay, don't worry, this is all coming back. It's just coming back prettier. So first thing we did was use PV equals nRT, right? And we got our moles of hydrogen. After we found our moles of our hydrogen, we converted them to water, right? So we converted them to moles of water using our balanced chemical equation. They just happen to be the same, right? 3 to 3. They just happen to be the same. They're not usually the same. Then we used PV equals nRT again to get to our volume of water. And then here's our moles of water. Here's our R. Here's our new temperature and our pressure. Okay, so things to remember. Remember when you ever use, so if you use PV equals nRT, the entire thing, this R is always the same. The units of it are liters, atmospheres, moles, and K, which means that your units need to be in, this has to be in liters. This has to be in moles. This has to be in atmospheres. This has to be in Kelvin, right? Or the problem won't work. So just remember that. And again, you don't need to memorize that. This constant's always given to you. It's going to tell you right here what units you need to have it in. So if you ever use this number, you must use the units behind it. Okay, ready for another one?
Professor?
Yes.
Are we showing all our work on our next exam for all the gas stoichiometry?
Yep. Yay. Make sure you leave yourself lots of room. Although I'm going to show you some shortcuts in a little bit. Okay, so I'm going to give you the balanced chemical equation, which I usually will give you the balanced chemical equation on your next exam also, and your next quiz, just because it's just too much if I don't. All right, so how many moles of H2SO4 form if 2.3 liters of SO3 gas is measured at 65 degrees Celsius in a 1.05 atmosphere? React with sufficient water. How many grams, question mark? Here's a balanced chemical equation. You see, when I read it like that, it's not very helpful, right? It's just like, oh, that's a lot of letters and that's a lot of numbers and I'm not sure what to do. So remember, this is your guide. You need to identify what you have and where you're going. What do you want? So you can see here, it says how many moles of H2SO4? Oh, okay, so we want moles of H2SO4. Okay. If 2.38 liters of SO3, okay, so 2.3, let me try and write that neater. 2.38 liters of SO3, and then we have a temperature, 65 degrees Celsius, and we have a pressure, 1.05 atmosphere. And oh, we also want grams of H2SO4. Okay. Well, what do we know? We know they're telling us about SO3, and they're asking about H2SO4. Okay, we have to get from one to the other. That's going to be a mole-mole ratio. So somehow we got to get to moles of SO3. Once we get to moles of SO3, then we got to convert it to H2SO4, and then we'll have that answer. And then moles to grams, that's just molar mass. We can do that one too. Okay, so here's the outline of what we're going to do. So we're going to use PV equals nRT. And again, how do you know we're going to use PV equals nRT? PV equals nRT. Let's look what we have. We have a volume, check. We have, oh, that's a temperature. We have a temperature, and we have a pressure, okay? And we always have R, so we can solve for moles, then we can convert from moles of SO3 to moles of H2SO4, and then we're good. Okay, so now I'm going to again, actually I'm just gonna leave all this in here. I think I can solve it all in one. Okay, so here's everything I just wrote. It's just prettier, of course. So let's figure out, let's do our moles of our SO3. So we have PV, I wonder if I have a room to do it over here. I have room here, I can try it. So let's solve for our moles here. Divide by RT, divide by RT. So N equals PV over RT. Our pressure, 1.05 atmosphere. Our volume, 2.38 liters. Our R, 0.08206. I'm not putting all the units. And I don't have my calculator. Hold on, let me get it. Temperature is 65 plus 273. .338 Kelvin. All right, and that's going to give us our N. Right? And remember, the whole reason we were trying to get to our N, which is our moles, is because this is going to give us our moles of SO3. Now, after that, we can just convert it to H2SO4. Mole-mole ratio. You can see it's a 1-to-1, so love those mole ratios when they're the same. So times 2.38 divided by 0.08206 times 338. And you get, I think I have this all right here for you. So much prettier this way. Yeah, 0.900 moles. By the way, I got 0.0900986. That's supposed to be a 0, right? And so at this point, people are like, oh, do I need to do my sig figs now? I mean, if you want to carry these through, you absolutely can. You don't need to necessarily round those sig figs until you get to the end. Okay, so now we have our moles of SO3. Well, it's a 1-to-1 mole ratio. So that's the easy mole ratio for us, right? It's 1-to-1. So we have 0.9 moles of H2SO4. Well, that was question number 1. Check. And then to go from moles to grams, we just use molar mass. And I'm just going to give you this one because, right, we're pretty good at this one. So we just used, again, this came from the periodic table, and we got 8.83 grams of H2SO4. Okay, so one thing about gas stoichiometry problems, they're never the same. So do not memorize, like, first I do this, and then I find V this way, and then I find N this way. It changes every single time. Like, there's a few of them that are the same, but you really have to just ask yourself questions. What are we starting with? What are we trying to get to? And then you find your plan on how to get there. Okay, so I'm going to show you one little baby shortcut here. Now, you don't have to use the shortcut. There's sometimes when you have to, but you don't have to. You can always use PV equals nRT the long way, but sometimes there's this nice little shortcut. And this shortcut is this right here. At STP. Now, STP means standard temperature and pressure. So standard temperature and pressure means 1 atmosphere and 273 Kelvin. So whenever you see this STP, this is just shortcut for these two things. So the temperature means it's 1 atmosphere, and the pressure means it's 273 Kelvin. I can't tell you how many times when people are like, I can't do the problem. They're not giving me the temperature and pressure. But then I'll just circle this. I'll be like, it says STP. Are giving you the temperature and pressure. Okay, so, and this is the shortcut. If we are at STP, meaning 1 atmosphere and 273 Kelvin, we have this conversion, 1 mole of any gas occupies 22.4 liters. Or I could have written it like this, 22.4 liters is 1 mole of any gas. Again, this is only at STP. So if I want to know the volume of gas of 2.2 grams of CO2 at STP, so I have grams, and again, I'm going to show you both ways you can do this problem. You don't have to use a shortcut. Shortcut's really nice though. So if you have 2.2 grams of CO2, and we have to go to moles. So if we do that, there's, I think it's 44.01 grams of CO2 in 1 mole of CO2. And it says we are at STP, which means this conversion holds. 1 mole of CO2 occupies 22.4 liters of CO2. And you get 1.12 liters. Shortcut, nice shortcut. The other way we could have done this, you could have used PV equals nRT. Because if we use PV equals nRT, we want volume, we have a pressure, it's 1 atmosphere because it says STP. Our pressure is 1 atmosphere. We have a temperature, it's at STP. Our temperature is 273 Kelvin. We always have R. We have a moles, we just have to convert our grams to moles, and then we could have solved for P. You get the exact same answer. It just takes a lot longer. This little lovely transition here, this little, little shortcut, this is really nice. But I want to remind you, only at STP. If it's not at STP, can't use it. Okay, so let's try this problem, and I'm going to let you try this one. So I gave you the molar mass, by the way, which you're going to need. So try and set this one up on your own. If you're watching this now or watching this later, set this up, see how far you can get so we can figure out what we need to fix before we can move on to the next piece. Okay, so try this, and then we're going to go over it together. How's everyone doing? Got it set up? This is no stoichiometry needed on this one, right? This one's a straightforward one. I'll give you another minute. So let me help you set this one up. So we want volume. We have grams.
Is 1 atmosphere equal to 760 mmHg?
Yep.
Thank you.
Yes, definitely gonna need that conversion. All right, I'll give you another minute and then we'll go over it. Okay, so if we look at this problem, we want to know volume, and we have, so we want volume. Oops. So we want volume. We have a pressure. We have a pressure. We want volume. We have a moles because grams, right? And we have a temperature. The only thing is that means we're going to use R. Since we're going to use R again, units, liter, atmospheres, moles, and K, this means this has to go to atmospheres. This always has to go to K. That has to be converted to moles. And then we can solve for our volume, right? So there's a lot of little conversions that we have. That's why I start with this problem, because it's going to get gets a little more challenging with all the small details. Okay, so let's first convert everything we need to do. And I gave you the molar mass. So the first thing we need to do is convert to our moles of our SO2 using our molar mass. So we're good there. So now I'm going to just change these. You see this right here? I'm going to change that up here so we can remember what we have. And then we need to convert our pressure to atmospheres, and that's our conversion. So we get to 80 atmospheres. And then we need to change our temperature, add 273. So this time I just added 273 instead of 273.15. Again, whichever one you want to use is totally fine. So now we have pressure in atmosphere, moles, and temperature. Now we can use our PV equals nRT. And so when we did that, PV equals nRT, we're solving for our volume. So divide by P, divide by P. So V is nRT over P. Oh, and I didn't change those up here. Look at that again. And we get 2.55 liters. And you see R this time, I used the 0.0821, the shorter one. Again, whichever one you want to use is fine with me. People seem to like this one better because it's less writing. That's fine. Your answer will be close enough. Okay, so questions on this one. This one had no stoichiometry on it. It just had a lot of little baby conversions. This was just a straight PV equals nRT problem. It just had a lot of conversions in it. So any questions on this one before we go? Ready to try another? Okay. Here we are. It's a real one this time. Okay, so this question says, how many liters of O2 at STP that can be made from the decomposition of 100 grams of PbO2? Interesting. Okay. So liters of O2, how many liters of O2? So that's what we want, right? We want liters of this. And it's at STP. Okay, remember STP, 273 Kelvin, 1 atmosphere. From the decomposition of 100 grams of PbO2. So we have 100 grams of this, and they're asking about oxygen. Okay, so we have a couple different ways to do this. We could do PV equals nRT, do our mole ratio, and then go over to volume. But this STP gives us a little shortcut. Remember, at STP, let me try and write that neater. At STP, 1 mole of any gas occupies 22.4 liters. Well, if I have a gram, I can convert that to moles, do a little mole ratio to oxygen, and then use this lovely little conversion here. Makes our problem a lot easier. Or we could do PV equals nRT, mole ratio, and then another PV equals nRT, but I'll do that. Let's do the shortcut way. So this is the same thing again. Here's kind of our plan that we're going to use, right? I'm giving you a molar mass because that's just almost silly for you to add these up at this point in time. So here's your molar mass. Just gave that to you. Okay, so if we start with 100 grams of PbO2, there's 239.2 grams of PbO2 in 1 mole of PbO2. Now I'm going to go from PbO2, right, all the way over to oxygen, 2-to-1 mole ratio. There's 2 moles of PbO2 to 1 mole of oxygen. Now we want liters of oxygen, right? In 1 mole of oxygen, there are 22.4 liters of oxygen. See that nice little shortcut there? It's like, I love that little shortcut. Again, it only works because it says STP. If it did not say STP, it would not have worked, right? And you end up with 4.68 liters of oxygen. Okay, so again, our little new piece here with that, but it only works because this was at STP. If it hadn't have said that, it would have been a much longer problem. So when you see that STP, you think, oh, can I use my shortcut here? It's much faster. Okay, so let me show you this all meter. Here it is so much prettier. Okay, any questions on this? So the shortcut pops up here and there, everywhere. Again, what you're looking for is those words STP. That's our shortcut. Okay, now we're going to introduce density to this whole fun stoichiometry world, but this density is actually not so bad. So remember that density is mass over volume. And so we can actually incorporate that in our problems. And so because density is mass over volume, we can actually use this little formula right here, which is the pressure density equals the pressure times the molar mass over RT. Now here's how we got that, but you know what? You don't need to know how to derive it. You just need to remember this little formula here, and we're going to use it. And I'm going to show you some other ways that you can use density too. Okay, so I'm going to show you even some better shortcuts for density. So since density is mass over volume, so just a quick reminder, all the densities we've been dealing with have been like grams per milliliter or grams per centimeter cubed. But when we deal with gases density are grams over liters, right? So that's just something to remember. So now if a gas is at STP, if it's at STP, right, we have our new little shortcut. If it's at STP, we know that density, again, is grams over liters. So this allows us to do this really cool, fun little shortcut. Moles cross out. So density at STP ends up being molar mass over 22.4 liters. And you can see how that works because the moles and moles cross out and we end up with density. But again, this is only at STP. If it's not at STP, you have to use the long one, which is right here. Okay, if it's not at STP. So let me show you a couple of these at STP just because it's kind of a nice little break for our brain to remember this one right here. So if we want to know the density of chlorine, and it says at STP, we can use the shortcut. Remember, density at STP is going to be the molar mass over 22.4 liters. That's kind of like the short remembering. I'll show you the whole thing right now. So Cl2 diatomic, it's 35.45, so that's like 70.9 grams per mole, right? And we have, remember, density equals grams over liters. So we want grams on top. Check grams on top. And then there's 1 mole in 22.4 liters. Moles, moles, liters on the bottom, liters on the bottom. That's how we find our density. We end up with 3.17 grams per liter. But you can see the shortcut here is 70.9 over 22.4, which is molar mass over 22.4. And that's going to be your density, 3.17 grams per liter. But here's the work that shows it. A lot of times people just remember this formula. It's fine. Whichever one you feel more comfortable with. Okay, so let me write this meter. So there's our conversion. And so you can see you end up with 3.17 grams per liter. Okay, so this is density at STP. Again, you can use that nice new little shortcut, which just shows you 1 mole over 22.4 liters. Okay, so here is one for you to try. Okay, so I want to know the density of nitrogen gas at STP. So try this one and then we'll go over it in like a minute. And then we'll go over this together. Okay, so I'm seeing a few of these already come through. So you have to look for your molar mass. Nitrogen's molar mass is like, I think it's 28.02. Yeah, 28.02. So when we do this, right, here's our little formula. So our density is going to be our molar mass, 28.02 over 22.4. And we end up with, 1.25 grams per liter, right? So let me just do that the long way. If we have 28.02 grams of N2 in 1 mole of N2, and in 1 mole of N2, there are 22.4 liters of N2, moles, you end up with 1.25 grams over liters. See, nice density, right? And again, here's just the shortcut, but feel free to do this either way. And we end up with 1.25 grams per liter. And again, remember, this is only at STP. Otherwise, we have to do it the long way, which we'll do a couple more of those. Okay, so now let's try another one. So remember how I told you that no problem is ever the same when it comes to gas stoichiometry? Here's another one. This one's not even gas stoichiometry. This one's just a straightforward PV equals nRT problem, but it's unlike one we've done before, which is going to continue to happen. So this question says, what is the molar mass of a gas if 12 grams occupies 197 liters at 3.80 times 10 to the 2 torr and 127 degrees Celsius. Okay, so let's just see what do we have here. So we have a mass, which is pretty much a mole, right? So hold on, let me try this. We have mass, which is 12 grams. We have a volume, which is 197 liters. Oops, That's supposed to say V. We have a pressure, which is 3.8 times 10 to the 2 torr. And we have a temperature, 127. I'm just going to write plus 273. Okay, so what is the molar mass? Okay, so molar mass. What's molar mass again? Remember, molar mass, the units of molar mass is the number of grams in, or grams per 1 mole, right? These are the units of our molar mass. So let's just see, there's pressures here, there's volume. So let's just check on PV equals nRT for this problem. Okay, so if we look at these, so we've got a mass, which I guess that might be the moles. Sure, maybe. Then we have a volume, then we have a pressure, and then we have a temperature, and we always have R. Wait, that doesn't make any sense, right? We can't have every single one of these. So we must be missing something. Okay, well, let's look closer. What does molar mass mean? Molar mass is the number of grams per moles. So if we look at this, we want to know the molar mass if 12 grams occupies volume, pressure, temperature. So volume, temperature, pressure. Well, and we always have R. What if we use this and solve for moles and put that there? And then what if this 12 grams is our mass? Well, that could work, right? And so this is what I'm talking about, how you're going to see problems that they're always different. It's kind of like a little puzzle, and you're always trying to fit the pieces of the puzzle together to make sure that it like makes sense in the end. Okay, so let's try this problem. Here it is. I'm just writing down everything we have already. So we're going to use PV equals nRT to get to N, and then we're going to use our N, or our moles, to get to our molar mass. Right, that's kind of our goal here. Okay, so since we're going to use PV equals nRT, well, this is in torr. We need to convert to atmospheres. This has to go to Kelvin. We're okay with volume, right? So, and remember, here's the conversion right here. 1 atmosphere is 760 millimeters of mercury, or 760 torr. Remember, they're the same. Millimeters of mercury and torr, same thing. Okay, so if we start this, first we have to convert and get rid of our torr. So this is going to become 5 atmospheres. So do that quick conversion. Do a little quick temperature conversion, right? Quick temperature conversion. And then I'm going to change those up here. I'm going to put those numbers at the top. So there we go. So now everything is in the correct units. So they're all in the correct units now. And then let's find our moles. Oops, that was not what I meant to do. So if we have PV equals nRT, we're going to solve for moles, divide by RT, divide by RT. N equals PV over RT. Our pressure, 0.5 atmospheres. Our volume, 197 liters. That's supposed to be a 9, sorry. Our R, I like to use the big R, the long one, it's fine. And then our temperature is 400 Kelvin. So when we do this, we get 3 moles. Now remember, they want molar mass. Molar mass is grams over moles. So that, therefore, if this is our moles and this is our grams, our molar mass will be 12 grams over 3 moles, right? And so I think I actually had this question on an exam, and the answers were, what is the identity of this gas? So it said, it gave you all, yeah, I remember. This was like 2 years ago on an exam. It was this question, but the question was, what's the identity of this gas? It kind of threw people off. That's why I put it on the lecture. What gas is this? How could you tell the identity of this gas? Yeah, you look on the periodic table. You look for the one that has a molar mass of 4. This is helium. Yeah, and the answer was like A, hydrogen, like B, CO2, C, argon, D, helium, right? And so all of that work for one multiple choice question. Hence why I put it in the lectures, because people kept getting it wrong. Okay, so let me just show you this meter. But I'm trying to show you that you're always going to see different things with these gas law problems. They're always changing. They're always changing. Okay. So, any questions on this one before we go? The key to this one was understanding what is molar mass, and that molar mass is grams over moles. That was kind of the key to this problem. All right, super fun one coming up. Super fun. .02 liters of oxygen is collected over water at 293 Kelvin with a total pressure of 755.2 millimeters of mercury. Find the mass of O2. Can anyone tell me what are very important words to this? This should be like, oh my gosh, these words are sticking out right now, right? And it's kind of the key to this problem. Anyone think about it? Yeah, this collected over water. When you see these words right here, this is a Dalton's law of partial pressure problem, right? So those words are very important because this is a Dalton's law. And remember, Dalton's law says that P total equals pressure of A plus pressure of B plus pressure of whatever. In this case, we have something collected over water, right? So we have oxygen collected over water. So in this case, we have its pressure of oxygen plus pressure of water, and P total equals that. Okay, so total pressure is 755.2 millimeters of mercury. P total is 755.2 millimeters of mercury. And then it says the pressure of water of that temperature is 755 torr. And remember, torr and millimeters of mercury, they are the same thing. So I'm just going to change that to millimeters of mercury. They're the same. So again, over water, that was the key here. This whole collected over water means this is step number 1. Step number 1, get rid of water. So this means that the pressure of our oxygen, minus 17.55, minus 17.55. So our pressure of our oxygen is 737.65 mmHgs, or torrs, whichever one you want to write. Yeah, so you got to subtract it. So basically, what's the gist of all this? If you see collected over water, you need to subtract your pressures. That's basically what we just did. If you see that, get out water. And that you're using, sometimes people are like, oh, but I'm just do that. What you're doing in your brain is you're using Dalton's law of partial pressures. You're subtracting out your water, you're getting rid of your water. So basically all we did was we took this 755 and we subtracted out our water. And that gave us 737.65. And that's our new pressure. Now we can start the problem, right? And again, it's that whole collected over water. That's the key here of starting this problem. Okay, so when we do this, first thing we have to do is get to our pressure. After we get to our pressure, this is a straightforward problem, right? We have a volume. We have a temperature, we have a volume, we have a temperature, we have a pressure, and we want mass, which is pretty much moles, right? We'll go from moles go to grams, we always have R. Straightforward problem at this point. So I'm going to do this first part. And then I'm going to have you try this one on your own before we try another one. So that was literally our first step right there. And we got to our pressure of oxygen. All right, so set this one up, try this one on your own, and then we're going to go over it in a couple minutes. So try this problem. Okay, so I'm seeing a few of them come through. So the first thing we have to do, right, we have to get this into atmospheres, right? Because again, if we're going to use PV equals nRT, we have to use liter, atmospheres, mole, and K, right? Now, how do we know we're going to use PV equals nRT? We have a volume, we have a temperature, a pressure, we want moles, which means we're going to have to use R. R needs to have these units, right? So yeah, we got to convert our atmospheres. And so remember our conversion here, 760, 1 atmosphere is 760 millimeters of mercury. And remember, we had to do the subtraction first. This was step number 1, right? Because of those words over water. We had to change our atmospheres. We had to subtract out water. So we got our atmospheres. Check. Now we can just plug in our PV equals nRT. So I just did all this right here for you. Here's our P, our V, our R, and our T. This gives us our moles. And from here, cross out our units. Then we can just use molar mass. And remember, it's O2, right? So the molar mass of O2 in 1 mole of O2, there are 32 grams of O2, not 16, because it's a diatomic. Okay, so we need this. We got 1.32 grams. All right, so let me just triple check the 75.2 minus 17.55 torr. Yeah, 0.97059. So if you didn't get this atmosphere, you probably just put something wrong in your calculator because the calculations here are right. So this is what you get when you subtract it. Again, the key, the first piece, that over water means we have to take, to get our pressure of our oxygen, we have to take 755.2 mmHgs, and we must subtract 17.55 torr. Right? That's what we have to do first, right? That's our very, very first step. 0.2 minus 17.55. So we get 737.65 mmHgs. And then we have to convert that, right? So we're not gonna use this pressure. We're gonna use this pressure right here. Okay. Now we're going to try another fun one. Okay, here you go. This is a test. So I'm gonna let you try this one on your own, the whole thing. I'm not gonna help you. And then we're gonna go over it in a couple minutes, but make sure you try and set this up. Don't just wait for me to solve it, because when I'm solving the problems, sometimes it seems like, oh yeah, that's how I do it. Yeah, that makes sense. Oh, I get that part, or oh, okay. But then when you do it on your own, you're like, I don't even know where to start, right? And so it's very, very, very important that you start this now. So when you get to your Chem 101 or your OLI quiz or your lecture or your exam, that you're not like, oh my gosh, what do? I don't know where to start, right? Because I can't take any of those for you. So try this now, and we'll go over this together. I'll give you a couple minutes to try this one. Maybe like 3 or 4 minutes. If you have any questions, again, you type in the chat, send me a text, and I can help you through them, or say it out loud and we can go through these. So try this, and then we'll go over it in just a couple minutes. Okay, so let's start this. Seeing a few come through here. So when we see this one, we see volume of oxygen. So it says what volume of oxygen? So this is what we want. We want liters of oxygen. And they're giving us a pressure, a temperature, and then grams of HGO. So, okay, grams of HGO, grams of this. I'm just gonna write 10 grams. All right, so no matter what, we can see we are starting with this. We need to get to oxygen. A mole-mole ratio has to occur here somewhere, right? There definitely needs to be a mole-mole ratio. Okay, so, well, if we have 10 grams of HGO, super easy to get to mole. That's not a G. HGO. It's really easy to get to moles, right? They give us a molar mass right here. 216.59 grams of HGO in 1 mole of HGO. So that's going to give us moles of HGO. Okay, so now we can convert that to moles of oxygen, right, using our stoichiometry. Then if we have moles of oxygen, we have a pressure, we have a temperature, we always have R, we can get to volume of oxygen. So this one, again, no, they're never the same. We get to our moles, do our mole-mole ratio, and then use our volume. Okay, so let's set all this up. So first thing we do is we used our molar mass, and then we used our mole-mole ratio. Again, 1 mole of oxygen, 2 moles of HGO to give us our moles of oxygen. And then again, now that we have moles of oxygen, we have temperature, we have pressure, all we need to do is solve for our volume. And I have all of this here nice and easy for you. Here's our moles of oxygen. Here's our R, our temperature. Here's our pressure, right? And we end up with 0.791 liters. And again, 3 sig figs there, 3 sig figs there. So we use 3 sig figs in the end. That's why we have 3 sig figs, 0.791 liters, right? So not so bad after you do a few of them. Kind of get used to the, like I said, it's like a puzzle at all times. Okay, cross off our units. All right, ready for one more? We're almost done. Just have one more left. Okay, here we go. One more. You're gonna try this one on your own again. Now this time I'm gonna throw out at you all sorts of different problems, right? Just like you're gonna see in Chem 101, and that's what you're gonna see in your OLI quizzes, all sorts of different problems all at the same time. Okay. How many moles of helium are found in a balloon that contains 5.5 liters of helium at a pressure of 1.15 and a temperature of 22 degrees Celsius? And this was a multiple choice question. Here would be your choices. Okay, so if this was on your quiz, your OLI quiz today, how would you do this problem? So I'm going to give you like 2 minutes, and then we're just going to do this one together. So try and set this one up, and then we'll do the rest of this together. Okay, so for this one, we have a volume. So again, we start everything with exactly the same way. PV equals nRT. We have a volume. We have a pressure, and we have a temperature. We always have R, and we want moles. So this is just a straightforward PV equals nRT problem, right? And so when we do this, a couple of quick things we got to change. We got to add 273 Kelvin to this, right? That's really our only change. And if we're going to solve for moles, divide by RT, and equals PV over RT. Our pressure is in atmospheres. Our volume is already in liters. Our R, again, whichever R, and then our temperature is 295. And when we do that, we get 0.26 moles. See, easy one, right? Straightforward, easy question. Maybe we have one more, time for one more. Okay, so 0.26, yes, great question. All right. Now this one's a really good question. And you're gonna see this definitely on your quizzes and your exams. There's a couple words in here that are very important. Does anybody see the words that are very important? That give us a great clue as to what to start and how to start.
Collected over water.
Yep, there it is again. Over water, right? Over water means this is a partial pressure problem. We got to subtract something out, right? So we only have 5 minutes. So I think I'll just walk you through this one just because we don't have a lot of time here. So it says how many moles, and then they give you a bunch of pressures. But no matter what, it says collected over water. When it says collected over water, that means before I even do anything, I have to subtract out my water, right? Number one, got to subtract out of my water. Because remember, P total is the pressure of, this one is, I'm just going to say A plus B plus water. So my pressure total is 758. So I need to take 758 torr, subtract out my water, which we already did this in a long way. So I'm just going to do it the short way. And torr or mmHg, they're exactly the same. So that's our very first step. We got to subtract it out. So 758 minus 17.54. And this number, by the way, it's always going to be given to you, the number that you have to subtract out. They always give that to you. So that means our pressure is 740.46 torr. Now we can start the problem, right? Whenever you see it over water, that's what you have to do first. Step one, subtract it out. Now we want moles. So if we have PV equals nRT, because this is the gas chapter, so what we're going to use. So this is what we want. We have a volume, check. We have a temperature, check. We just found our pressure, check, right? And we always have an R. So now it's a straightforward problem. So if we divide by RT, N equals PV over RT. Our pressure, unfortunately, we have to fix. Right, got to fix that. So divide by 760. I got 0.974. So our pressure is 0.974 atmospheres. Our volume's in milliliters. 1, 2, 3. That's 0.5 liters. However you do these conversions at this point, it's really personal choice to you. I'm not going to make you do them one way or another. You have already developed a way that works best for you. And our temperature, 20. I got to fix that one too, right? 20 plus 273. 293. And then we just plug them all in. Right, so that's basically, straightforward problem after that little tiny twist at the beginning. Divided by 0.08206 times 293. So I got 0.0203. When I plugged all that in. Okay, so again, this was that Dalton's Law partial pressure problem right here we talked about last lecture. Okay, so any questions on this? So we are done again this week. All you have is your OLI gas laws. Feel free, by the way, we've finished gases pretty much. So you can do all of your Chem 101. There's nothing left for us to do in gases. You can do all of your OLI if you want to get ahead. You can do all of your Chem 101 if you want to get ahead, because we're pretty much done with gases. We've covered every single principle that we've got. So feel free to finish it if you've got extra time this weekend. Since you don't have a quiz, you've got some extra time. And then also you can get ahead so you have less to do during Thanksgiving too, because your next exam is just stoichiometry and gases and stoichiometry. So we've covered everything up until up to your next exam. So you can start studying and then you can take your exam earlier, because remember, we're opening it a week early. So you have the whole week of Thanksgiving to work on it this time. So you could finish it before Thanksgiving if you choose, because we are now done with the material. Okay, done with the material up until your exam. Okay, so any questions before we finish today? No questions?